Hi everyone and welcome back. Today we're going to be covering combined gas laws. So combined gas laws are just used to predict how a gas behaves when pressure, volume, and temperature changes. So our formula for this is P1 times V1 over T1 equals P2 times V2 over T2. So P stands for pressure, V stands for volume, and T stands for temperature. Now, the one in our first side of the equation, it just represents our starting amount, our starting values. And then the 2 is just like the afterwards, so how it changed. So before that, we're going to go into the relationships between pressure, volume, and temperature. So the first relationship that we're going to cover is pressure versus temperature. So pressure and temperature have a direct relationship. So it's going to look something like this. So we have our graph here, right? We have temperature here, and we have pressure here. So as temperature increases, pressure is also going to increase. Now I'm going to tell you why. So here we have a container. The volume does not matter. That's going to stay constant because what we're looking at is a relationship between pressure and temperature. So when we're looking at our actual formula, right, we're going to ignore the volume. So it's just going to be P1, right, and T1. So we're not including the volume because the volume, again, it's staying constant. That's not a factor that we're looking into. And then P2 over T2. So again, we're looking at the relationship between temperature and pressure. So as temperature increases, pressure is also going to increase. So again, it's like a positive correlation. As one increases, the other one increases. Now the reason being is because whenever we heat up, right, a container, the particles within that container are going to move faster. And when that happens, it creates more pressure because now they're all hitting each other more. So looking back at our container, right, since we can't change the volume, when these particles start to collide more frequently due to the increase of heat, all that pressure is just going to increase. So think of it, here we have our particles, right? Now when we increase the temperature, right, let's say I have a little flame right there. It's increasing the temperature, right? So they're going to start hitting each other, right, more frequently, colliding because of the increased heat. But however, since the container stays constant, the size cannot change, the gas or the molecules inside cannot relieve this force. That's why the pressure inside of it is going to increase. It's like a balloon, except the balloon isn't being filled up with air because the volume is changing. But in this case, the volume is staying the same. So that's why we exclude the volume portion of the formula. Now, number 2, volume versus temperature. So now since here we're talking about volume and temperature, we're going to disregard the pressure. So this is not going to be included in our formula. So this is also a direct relationship. So again, as one increases, the other one increases. So volume and temperature, it's going to look like this. V1 over T1 equals V2 over T2. Something that you should take away from this is that whatever stays constant, you can disregard it from the equation. And you just focus on what's directly being impacted, right? The direct relationship. So in this case, it's volume and temperature. So one increases, the other one increases. So our graph is going to look basically the same as the one above. Temperature and then volume. So it's going to increase this way. So here we have another container, right? So we have our particles in here, and we're going to increase the temperature. Now when we increase the temperature, again, the particles are going to collide more frequently. And when this happens, they're going to move more fast, right? And they're going to hit the walls around the container more frequently as well. And eventually, in order to keep the internal pressure constant, or therefore it's going to match the unchanging outside pressure, the container is going to need to expand. So it's going to become bigger. Because again, all the particles inside are moving. They're moving very fast because of the increased temperature. So they're just going to be colliding everywhere. And eventually, the volume is going to increase until the particles travel further to hit the walls, ultimately lowering the collision frequency back to balance the pressure. So whenever we increase the temperature, the particles collide more frequently, they hit the walls more, causing the container to expand, and therefore the volume increases. So you should take away that heat increases kinetic energy, and therefore more collisions. Now our last relationship before we get into the practice problem is volume versus pressure. So volume versus pressure actually has an inverse relationship. So the way that it's going to look like is we have volume here and pressure here. So as volume increases, pressure is going to decrease. So since in this case we're looking at the relationship between pressure and volume, we're going to ignore temperature. So the equation is going to look like this. It's going to look like P1 V1 equals P2 B2. So once again, I want you to think of the container. Let's say we start off with a small container. If the volume of this container increases, so there's more space inside, the particles inside won't be as clustered anymore. So they're going to have more space to roam around. So therefore, the pressure inside this container is going to decrease because now they have more space. So now let's do this practice problem. The pressure of a gas changes from 120 to 50. The volume changes from 45 to 40. If the initial temperature is 354.15 Kelvin, what is the final temperature in Kelvin? So let's look at the information that we know. So we know that our starting pressure, right, because it's saying that the pressure changes. So the starting pressure, which is P1, is 120. And then it says it changes. So then our second pressure is 50. Then it says the volume changes from 45 to 40. So the first volume is 45 and the second volume is 40. And last but not least, it says the initial temperature is 354.15. So that is our T1, 354.15. And asking for the final temperature. So that's what we don't know. We don't know what T2 is. So we're going to leave that as X. So now we just plug these values into our formula, which is, again, I'll just rewrite it, P1, V1, T1, P2, V2 over T2. So we know that P1 is 120 and V1 is 45. Oh, we know that T1 is 354.15. Now for the next slide, we know that P2 is 50 and V2 is 40. But we're solving for this missing temperature. So we can do the butterfly method, right? Where we do 120 times 45 times x. So that's going to give us 5,400x is equal to 354.15 times 50 times 40, which is going to give us, and we're going to get 708,300. So then we're going to divide 5,400 on both sides, and we're going to get x is equal to 131.17 Kelvin. Now for our last problem. A sample of neon experiences a pressure drop from 75 to 53. The temperature increases from 27 to 93. If the initial volume is 12 liters, what is the final volume? So let's write down the information that we know. So we know that the initial pressure is 75, and then the second pressure is 53 when it dropped down. Then our initial temperature is 27 degrees Celsius, and our second temperature is 90 degrees Celsius. And then initial volume is 12 liters, and we're looking for our missing volume, the final volume, because that's what we don't know. So I'm just going to rewrite the formula, which is P1, V1, T1, and then P2, V2, T2. Now before we start solving this problem, we need to convert the temperature, which is in degrees Celsius right now, into Kelvin in order for this formula to work. So if we look at our reference table, the formula to do this is K equals degrees Celsius plus 273.15. So that's how we're going to convert the degrees Celsius, which is our temperature, into Kelvin. So we're going to do 27. So this is for T1, 27 plus 273.15. And we're going to do for the second temperature, 93 plus 273.15. And we're going to get 300.15 for this one, and then 366.15 for this one. And these values are going to be in Kelvin because we just converted them. So now we can plug these values into the formula. So P1 is 75 and V1 is 12. But then T1, since we converted it into Kelvin, it's going to be 300.15. And then P2 is going to be 53 times V2, which we are solving for. And then T2, since we converted it into Kelvin, it's going to be 366.15. And then we just do cross multiplication on both sides. We're going to get 329,535 is equal to 53 times 300.15 times x, 15,907.95 x. Then divide that on both sides to isolate the x. And we're going to get 20.7 liters. Therefore, the final volume is going to be 20.7 liters.